Hello everyone. Last time we introduced limits. We did some with polynomials, we did some with radical functions, we did some with rational functions. But there's a type of function that we spent a lot of time working with this year, pretty much most of the first half of the year, that we can also take limits of, and that's trigonometric functions. Now, of our basic trigonometric functions, it's very straightforward to take a limit. If you were to do the limit as x approaches a of, say, sine of x, well, if you're doing the limit as x approaches a has to be a member of the domain of sine, and the domain of sine is all real numbers. There are no discontinuities in sine of x. And since there are no discontinuities, there are no issues with just plugging in a. So that's cool. And even if you chose a specific value, like say 0, it would just be sine of 0, which we know is 0. So just our general trig functions, it's going to be straightforward. It's going to tell us you just need to plug it in as long as a is a member of the domain. So if you had something like the limit as x approaches pi over 2 of tangent of x, that limit would not exist because pi over 2 is not a member of the domain. You wouldn't be able to plug it in. And there's the vertical asymptotes happening there. Remember, at pi over 2, it would behave like this. So we wouldn't even be able to say infinity or negative infinity, because on either side, the right side limit is going down, the left side limit's going up. So you wouldn't even be able to say positive infinity or negative infinity. But sometimes there's going to be limits where you can find even though you can't plug it in. So let's say we had the limit as x approaches 0 of a manipulation of sine of x, where we did sine of x over x. If we were just to plug it in, it will be sine of 0 over 0, and sine of 0 is 0, so it's 0 over 0. Now, if you are evaluating your limits and you plug it in and you get 0 over 0, most of the time you are actually going to be able to find the limit. This is what's called an indeterminate form. I don't think I left myself enough room. Ooh, barely. This is an indeterminate form. This relationship, it follows a bunch of rules, but it doesn't work for any of them. If you have 0 divided by anything, it should be 0. But you're dividing by 0, which you can't do. That's impossible. You can't divide by 0. So that's two rules that don't work. And then if you have something divided by itself, shouldn't it equal 1? 8 divided by 8 is 1. 32 divided by 32 is 1. But 0 divided by 0 is not 1. So this, just by itself, it breaks 3 rules that we know pretty hard and firm. So that's why it's called an indeterminate form, because you're not able to determine anything from that. Now, next year, you're going to learn a way to evaluate these limits more directly. But for now, we're just going to use our calculator. So I want my calculator to be in radian mode, just so I have smaller values of x that we're working with. I'm going to set this up as sine of x divided by x and y1, and make sure my table set is for ask, and it is. And I want numbers close to 0, but not 0. Because if I plug in 0, it gives me an error. It gives me a read error there. See there, you can see. So I'm going to choose numbers to the left and right of it. And if they seem to be approaching the same value, then that value is going to be the limit. So if we had like 0.001, 0.0001. So these are all really, really close to 0 on the positive side, and they're yielding 1 every time. So at least we know that the right-hand limit is 1. But if we try the others from the other side, negative 0.001, negative 0.00001, and just hammer on the zeros. All right. Oh, look, it gave the same thing. We have the same result on either side. The left side is approaching 1 and the right side is approaching 1 as our x gets closer and closer to 0. So that means the limit as x approaches 0 of sine of x over x equals 1. And I'm also going to just show it in the graph. I'll change my window, make it a little better. So x-min, I'll just do negative pi, and then pi. And y-min, I'll do negative 2 and 2. So if you see, we've got that smooth curve, but because of this divide by x, we have a hole at 0. But that hole is at 0, 1. So the left side and the right side are both approaching 1. All right? This is a general rule for taking a limit of a trig function. This helps us find out any trigonometric limit where we have that indeterminate form. Okay, so anytime you have trigonometry inside your limit and it yields 0 divided by 0, if you're substituting in, then you can manipulate it to this. So what if we had instead of sine, what if we did the limit as x approaches 0 of cosine of x over x? If we substitute in, we'll plug in 0 for x, cosine of 0, and the cosine of 0 is 1. This is just 1 divided by 0. This isn't an indeterminate form. This just means there is no limit. It might be going up to infinity or down to negative infinity, but there's going to be an asymptote there. And both ends could be going up, both ends could be going down, but that doesn't mean that the limit exists. It's not approaching a real number. We just we just use the terminology for limits to make it easier for us. If it's approaching, we'll say infinity or negative infinity. So this one, no change, you're just never going to be able to do it. But what if we want to produce that as a 0 over 0? Well, we have the 0 in the denominator. And if we need to make a 1 a 0, we need to subtract it from 1. So the limit as x approaches 0 of 1 minus cosine of x over x. If you plug in 0, it's 1 minus cosine of 0, which is 1, over 0. That's 0 over 0. That's that indeterminate form. So what we want to do is we want to somehow use the limit as x approaches 0 of sine of x over x to make this make more sense. Well, we don't have any sines here, but we have something close to a sine. We have that 1 minus cosine of x. And 1 minus cosine of x, if you multiply by its conjugate, you get 1 minus cosine squared of x, which we know is sine squared of x. But you can't just do something to the numerator and not do it to the denominator, So we have x times 1 plus cosine of x in the denominator. So this limit says the same thing as that, because we multiply top and bottom by 1 plus cosine of x, and it says the same thing as that. Oh, so now we have a sine of x in the numerator and x in the denominator, so we can separate this out. We can say the limit as x approaches 0 of sine of x over x times, well, there's 2 sine of x's in the numerator, and then there's an additional 1 plus cosine of x down there. So if we multiply these two ratios together, we would just produce that again. And last week we determined that if you have the limit of a product, it's also the product of the limits. Wait a minute. We know that limit. That's just 1. And this one, let's try plugging in and see if it works. And if it does work, then we're all set. We don't need to worry about discontinuities or anything. So if we plug in 0, sine of 0 is 0. And 1 plus cosine of 0 is 1, plus 1 is 2. So it's 1 times 0 over 2, which is 0. So the limit as x approaches 0 of 1 minus cosine of x over x is just 0. Now there was one more trig function that we spent a lot of time with, and that was tangent. So let's try the original form where it's just tangent of x over x. It worked for, it gave us a limit for sine. It didn't give us a limit for cosine. But let's try here. Tangent of x, if you plug in 0, is 0. And 0 is 0. Oh, it's that indeterminate form. So that means it's most likely going to have a limit there. Most of the time, if you get that indeterminate form, when you plug it in, it's actually going to have a limit. You'll understand that more next year when you learn about something called L'Hopital's rule, but we're not covering that this year. That's a calculus thing. So let's try it. Let's try and manipulate this one. Well, we know an identity for tangent. Tangent is sine over cosine. So that's sine of x over, and then if you're dividing by x, it would be x cosine of x. Well, now we have the sine of x over the x. So that's sine of x over x times 1 over cosine of x. And if we multiply those out, we would just produce that again, which is the original. And we have a limit of a product, so we can treat it as a product of the limits. X approaches 0 of sine of x over x times the limit as x approaches 0 of 1 over cosine of x. Well, we know the limit as x approaches 0 of sine of x over x, that's 1. And if we plug 0 into here, cosine of 0 is 1. 1 divided by 1 is 1. So this one is just 1. So if we encounter limits with sine, cosine, or tangent that produce these indeterminate forms, 0 over 0, we can manipulate it using these 3 rules. The limit as x approaches 0 of sine of x over x equals 1. The limit as x approaches 0 of 1 minus cosine of x over x equals 0, and the limit as x approaches 0 of tangent of x over x equals 1. So we have these three rules. Let's just try an example. Let's say we have the limit as x approaches 0 of sine of 4x over x. If you plug in 0, 4 times 0 is 0, sine of 0 is 0, and then divide by 0. So it gives us that indeterminate form, which means we should be able to simplify this somehow to give us that relationship, to give us an actual limit. Well, our rule for sine is this one. If you notice, the angle and the denominator are exactly the same. That is not what's happening here. So in order to use this rule, we need those to be the same. So there's a couple ways to approach this. One way to approach it is to use substitution. So let's let theta equal 4x, which would in turn mean that x equals 1/4 theta. So if theta equals 4x, we can replace that. We can say the limit as x approaches 0 of sine of theta, and replace that x with 1/4 theta. But then we have an x here and we have those. So it really would be 1/4 theta approaching 0. Well, if 1/4 theta is approaching 0, isn't that going to be at the same place where theta approaches 0? Because that's a linear function and it's approaching 0. So you could just say as theta approaches 0. We don't want fractions of fractions. I'm going to simplify that. So multiply top and bottom by 4. And then that's just a scalar. Oops, I want to bring that outside the limit. And we talked about how you can just bring a scalar outside the limit. And that's 4 times 1, which is 4. That's the more complicated way to think about it. Next year, there will be limits that you're solving where you will need to redefine the variable. But that's the more complicated way to look at this. If you want the easier way to look at it, you just need to think about how you can make that denominator look like that numerator. Or I'm sorry, look like the argument of the sine. And to do that, you just need to multiply it by 4. So you multiply the denominator of this fraction by 4, but you can't just multiply the denominator of a fraction. You need to multiply also the numerator of the fraction. Now, as long as this matches that, it's the same rule. It's the same rule as this. Because when 4x approaches 0 is the same place where x approaches 0. So it's the same rule, so it doesn't matter as long as these two match up. And now they do. So we can take out that 4, limit as x approaches 0 of sine of 4x over 4x. So that's 4 times 1, which is 4. So you want to make your denominator match the argument. And same thing whether it's a cosine or whether it's a tangent. All right, that's pretty much it. Hope you guys have fun.